We're given a diagram here where we've got a turbine. Head extracted by the turbine, which is denoted by CR, is 200 feet. So 200 feet of head is extracted. And the pressure at T, which is up here, is at 72.7 psi. For losses, we're given head losses between W and R and between C and T. Determine how much water is flowing in the pressure head at R. We're to assume that water is a working fluid, it's incompressible, and the datum is at CR. Notice that they give us an elevation of 100 feet, so we need to keep a count of the relative elevation changes. So this is 50 feet, and this is 150 feet difference in elevation. Notice we have 12-inch diameter pipe and 24-inch diameter pipe at the outlet. So we've got water coming down, running through a turbine, generating energy, generating power, and then going into this this tank. So let's put some given information in. So I've got some elevations, I've got the diameters, I've got the pressures. This is the head from the turbine that's being generated, and I'm using a nominal density of water of 1,000 kilograms per meter cubed. I'm going to apply the Bernoulli equation from T to W for the flow rate calculation, and then the pressure and velocity and the at position W are going to be zero, negligible, respectively. So let us bring over the general Bernoulli equation. So what have we got? We're going to apply this between T and W, right? We need to know what the flow rate of the water is. Head added, there's no pump, right? Head loss, we're told what the losses are. We've got losses between W and R, and so 2 velocity heads between W and R, 3 velocity heads between C and T. All right, head extracted, that's 200 feet, so that's what the turbine is. And then we've got our pressure term at, notice that we're going to have a pressure term at P1, right, or at PT. Are we going to have a velocity term at position 1 or T? Yes, we will. We will also have Z, and then we will have a pressure term at W. No, we will not, because we will be working with gauge pressure. So that's going to be 0. The velocity at position 2 or W is also going to be 0, and then we're going to set our datum. If we set our datum here or here, depending on how we set our datum, how are we going to do that? ZT, we're going to set that at 250. ZW is going to be 150. So we're just going to we'll use the absolute. If we wanted to, we could set that at 0 and then set that at 100. But that's how we'll handle this. All right. So once we make all those simplifications, what are we left with? Well, we're left with PT, the pressure head, velocity head, and the elevation head, minus the head loss, minus the head extracted, and I'm going to call this CR because that's what the problem statement calls it. That is equal to, the only term that we're left with on the right side is the elevation head. So remember what we did for another problem. We need to solve for remember, we want to find the flow rate, the volumetric flow rate, and so we can, where's the volumetric flow rate in here? Well, it's not, we don't see any Q's, but it is incorporated in the velocity, right? It is incorporated in the velocity, and so our head loss in terms of velocity, we can express that in terms of volumetric flow rate. We can also express V sub T in terms of volumetric flow rate. So let's go ahead and do that. So our head loss, we have 3 velocity heads from T to C and 2 velocity heads from R to W. And so when we substitute in for our volumetric flow rate, this is what we get. And then we can take our Bernoulli equation, our simplified Bernoulli equation, and substitute those terms in. And what I've done is I've moved everything over to the left so that everything is equal to 0. And I now have one equation and one unknown. My one unknown is a volumetric flow rate. Again, it's a quadratic equation. The easiest way to do that is in MathCAD, where we use the root finder, where I provide a guess. And here I put a guess at 20 cubic feet per second, and then I ask MathCAD to find the root of this function for Q, and I get a volumetric flow rate of 35.56 cubic feet per second. So that is a flow rate of water coming through this turbine. All right. So now I want to calculate the pressure head of the turbine at R. So let me bring over a smaller version of this. I want to calculate the pressure head at the outlet of the turbine. So we can apply the Bernoulli equation between T and R, or we could apply it between R and W. So I'm going to apply it between R and W first. So let's see what we get with that. So if I apply the Bernoulli equation between R and W, and the reason why I'm doing that is because it looks like it's going to be easier, right? So I take my Bernoulli equation and I say, okay, I will need a pressure head term. I will need a velocity head term. My ZR, I'm just going to leave it as ZR for now. All right. And I have a head loss term between R and W as well, right? What about on the right side? Do I have a pressure head on the right side of the equation at W? No, I do not, because again, we're using gauge pressure. This is open to the atmosphere, and so our gauge pressure is 0. What about velocity head? No, we do not have a velocity head here because the level in the tank is going to be moving up and down, or actually up very, very slowly. So no velocity head. All we're left with on the right side is our elevation head. So this is what we have here. We can plug everything in, and so here is we know what the volumetric flow rate is, so we can calculate the velocity at R in this pipe. So this is our velocity in the pipe, and again I'm using what the elevations here, so the relative difference is 50. So I'm using the relative difference, and so now I can also add in the head loss between R and W. And so I know what the velocity is, calculate the head loss, it's 3.982 feet. And so I can calculate what the pressure is. All right. So the pressure at R, and again, this is what I have here, and I'm putting this in terms of pressure head. The pressure head at R is equal to this, which is 51.99 feet, or about 52 feet. If I want to calculate, so that is the pressure head. If I wanted to actually calculate the pressure, I would take the pressure head and multiply it by rho g. All right. So the pressure head, what I'm doing is I'm defining it as this term. All right. So the pressure head is PR over rho g. That's what this term is here. So it's 51.99 feet. And if I wanted the actual pressure, I could just multiply by rho g, and I get 22.5 psi, or 155 kilopascals. What if I wanted to do the pressure head calculation between T and R? Well, I could do that as well, and I should get the same answer. So let's take a look at that real quickly. The Bernoulli equation, here's a bunch of information that is calculated or already entered and repeated for convenience. Here's my Bernoulli equation. Yes, I do need the pressure head at T. Yes, I do need the velocity at T. Yes, I do need the elevation. I do need the head losses between T and C and R. What about the pressure here? Yes, I do need pressure here. Velocity, yes. Elevation, yes. So I do that. Notice that I get the same pressure. If I solve for pressure, I get the same pressure that I had up here. If I convert that pressure to a head unit, I get the same pressure head. So same answer. So that's good.